Math 98. This is a video for what we did yesterday and today in your classes. It's lesson 3.4. So for those of you who were not able to be online for that, I'm going to go over it now. Alright, so lesson 3.4, we're talking about braking distance. I'll let you read the problem situation on your own. But braking distance is the distance that your car travels between the time you apply the brake and when the car actually stops. So you know that when you apply the brake, it doesn't instantly stop, right? So the first thing I'm going to ask you to do in question 1 there is think about what are some variables or what are just some things, some conditions that might affect how quickly your car stops when you hit the brake. So just think about that for a second. On number 1 there, just you can write down a couple things. And I'll write down some up here that have come up as we've talked about this in class. So some of them are how good your tires are. If your tires are better, you'll stop sooner. If your tires are getting bald, means there's not as much tread, then you'll slide a little more. The road conditions, and that can be weather related, like are they wet or dry? Or it could also be, is it gravel versus asphalt? If you stop your car, or even a bike, think about a bike if that's more familiar to you. On gravel, you're going to slide a little more, right? Where on asphalt or blacktop, you're going to stop. Again, if it's icy, think about if you have bad tires on an icy road and you hit the brake, you're just going to keep sliding. If you have good tires and the road is dry and a really nice surface, then you'll stop much sooner. The other thing is the steepness of where you are. So, if you're going uphill, downhill, straight, that can affect it. And also, the other thing is speed, okay? So if you're just kind of creeping along at a couple miles an hour and you go to stop, you'll stop very quickly. If you're going 70 miles an hour and you go to stop, it'll take you longer just because of inertia, right? Your movement keeps going. So those are some variables that could affect the braking distance. And so these things, in this lesson, we're going to be dealing with a formula for braking distance, and these things are in that formula, okay? So you'll see that. So as they change, your distance to stop changes also. All right, so in number 2, it says you'll examine a variable that affects braking distance, which is speed. So when we're looking at when we're trying to do an experiment, right? If I were trying to take some cars out on different roads, different conditions, and see how the braking distance was affected by different things. Let's say I take my car out and it's a nice day, I have a nice road, I have good tires, and I'm driving 25 miles an hour, and I measure what my braking distance is, okay? Now, then if I could take that same car out on an icy day, not great road, bad tires, and I'm going 50 miles per hour, my braking distance is going to be a lot longer. But it's hard in those two situations to know what changed, what made the biggest change, right? Well, not only did I go from slower to faster, but I also went from good tires to bad tires and a good road to icy, and all these things changed. So if we're doing an experiment, we only want to change one thing at a time. So I might say, okay, I'm on this good road, good tires, going whatever I said, 10 miles an hour, 20 miles an hour. And then to experiment with that, I might say, okay, now I'm going same road, same tires, now I'm going to go 50 miles an hour. Now I know that whatever difference there was in the braking distance must be because of that speed, if everything else is the same, right? So we don't want to change everything at once. So here what we're going to do is we're going to have a constant, keep some things constant in terms of the tire, the road conditions, the way that this factors into it. The only thing we're going to change here is the speed. So in number 2, it says you can think of some specific questions, but when we do this in class, even, we always do the same question. It's just a little bit easier, and it also demonstrates something else I want to show you. So we're always going to do that first example one, what happens to the braking distance if you double the speed. So we don't have to really write anything down for that right now. That's going to be what we get to in a minute. So then if you look at the next page, you can see the formula for braking distance. So the first thing is to not panic, okay? Because It looks a little crazy, and lots of stuff here, lots of variables. Okay, now remember that a variable, like these letters, is something that I can plug in for. So this D is my braking distance. Okay, that's what I'm going to get out after I plug in for these other things. So you can see under this formula, it mentions what each of those variables stands for. And the variables in the description are not in the same order they are here. I don't really know. They're sort of in a random order. I'm not sure why. But here's my braking distance in feet. V sub 0 is what we call this. That's my initial speed or velocity. V for velocity, but it means speed. 0 just means like at time 0. Like right when I hit the brake, this is what my speed is. Obviously it's going to slow down until I stop, but this is the speed when I hit the brake. That is squared. G is actually a constant amount, and it says that in there. It's 32 feet per second squared. Okay, so let me talk about what this is for a minute. This is the acceleration due to gravity. So we know if I go up to the second floor of a building and drop something out of it, gravity's going to have it fall to the ground, right? Well, what actually happens, and you might remember hearing this in a physics course or something, is that that item, let's say I drop a penny, that penny is not going to fall at the same rate all the way down. It actually gets faster and faster and faster as it falls. Okay, so it accelerates, it gets faster. Acceleration due to gravity. So this feet per second squared, another way we can think of it is feet per second per second. So feet per second is a speed, right? So that penny goes 32.2 feet per second faster every second. So when it starts out, if the first second it's going, let's say, 10 feet per second, the next second it's going to be going 42.2 feet per second. And the next second it's going to be going about 70 feet per second. It's going to add on this much speed every second. Okay, so this squared is part of the unit, so we're not going to actually square that number. Now the reason they didn't just put 32.2 in here and they have this variable is because this number is constant, but we could use different units. So another way that it's sometimes described is in meters per second. It would be 9.8 meters per second squared. So depending on whether you're using meters or feet or another length unit, this would be different. You'd have to pick from which value it is. Okay, so this is, in our case though, we're going to be doing all feet per second, so that's going to be there. Little f is my friction between the tires and the road. So f is going to be between 0 and 1. Okay, and really simply, 0 is really bad and 1 is really good. So 0 is bald tires on an icy road. You go to stop, hit the brake, and you just keep flying for feet and feet and feet. Okay, this is really great brand new tires on a dry, brand new road. You hit your brake and you stop really fast. Okay, so it's going to be in between there. So think about numbers between 0 and 1. It's going to be point something. Okay, in our case, it's going to be 0.8. So that friction, I mean, we don't know exactly what goes into that, but they, to figure that out, they look at the road conditions, the tires, all that stuff, put it all together. And then G is the grade or the steepness of the road. And that's going to be given to us too. So if we look at number 3, at the bottom, it says let f equal 0.8 or 8/10. So f is going to be this, and g, capital G, is going to be 0.05. Okay, so we know these two things, and we know that little g is 32.2. So again, we're going to have values for these three that stay the same, so that in our experiment with our data, we can just change speed and see how that changes the braking distance. So the first thing you're going to do is you are going to write a simplified version of this formula with these three pieces of information in. So we're not doing anything with that velocity yet. So what you're going to do is you're going to substitute in each of these numbers where they go here and then simplify it to have one number. So we're going to have one number here. So you're going to have 2 times 32.2 times 0.8 plus 0.05. So go ahead and take a minute to do that. So you're going to substitute in for those and then simplify. Okay, so we know from orders of operation, we want to do what's in parentheses first, right? So I can make this a little bit simpler and more simplified by saying 32.2, and then this is 0.85. Now I just have three things that I'm going to multiply. Okay, so we can multiply these together. Hopefully you have gotten 54.74. Now, your F and your G actually don't have units on them, so it kind of picks up the units of that little g. So technically this is going to be feet per second squared is your units on the bottom. And if you think about that, you can kind of see this would be second square, or this would be feet per second also, and I would have that whole thing squared. Don't worry as much about the units here because they get a little tricky, but I'm just going to take them out, okay? But we could figure out the units here will cancel out in such a way that my distance is just in feet. Okay. I'd have feet squared per second squared on the top, feet per second squared on the bottom. Don't worry about the unit stuff. They just get a little messy. But this is a simpler formula when my friction and my grade of the road are kept constant, and using the acceleration due to gravity as the 32.2 because I'm using feet in seconds. Okay, so once I have this, since these things are constant, now I can just plug in different values of speed, initial speed, and then I can do what I need to do here to simplify it, and then I can get out the distance. All right, so let's go ahead and say we want to do 5 first, and this is in miles per hour. Okay, so my first piece of information, or my first little setup, like a little experiment or whatever, is going to be at 5. We're going to be traveling at 5 miles per hour, and we want to know how far my car travels still after I hit the brakes at 5 miles per hour. Okay, now, there's only one problem with that. If you remember over here, we have everything in feet per second. So I can't plug in 5 here and have this be miles and hours up here and have this be feet and seconds down here. It doesn't mesh together, okay? It's trying, the whole idea of like apples and oranges, right? So I can't do that. So I need to have my speed, I need to change it to feet per second. So think about the texting question from a couple lessons ago, right? Where if you look down for 4 seconds, you're traveling, I don't remember what it was, 60 miles per hour or whatever. How many feet per second is that? It's just another way of measuring. So I'm going to need to use that. So I need to convert my speed from being in miles per hour to being in feet per second. So hopefully by now you're thinking, oh, a conversion from one unit to another, I'm going to use dimensional analysis, right? Okay, so that is exactly what we're going to do. We want to go from 5 miles per hour, and we want to know how many feet per second that is. Okay, so I'm going to stop this video, so I'm just about out of time with it, and then I will start another one. We'll pick right back up here. Try to set this up before you start the next video, okay? I know you can do it. Think about what you're ending up with for units and how I get there.